but also a feeling of tremendous power and possibility.
I think there was a kind of an optimistic peak, if you like, in terms of what we thought technology and science could do, probably in the middle part of the 20th century, in the 50s, say. And I suspect that was associated with all sorts of technological developments, but also with a sort of cultural optimism that came probably after the Second World War, the idea that technology was going to solve a lot of the problems that we had previously.
In the 1950s, the future was going to be a planned utopia of wide boulevards and shining skyscrapers, where we'd all be happy and prosperous. And the engine of this new prosperity and certainty was to be the computer.
Just as the telescope had let us see the heavens, and the microscope the building blocks of life, so the computer promised to let us see into, and maybe even control, another dimension, the future. James Lovelock remembers those heady times.
There was that wonderful sense of certainty in those days about everything. Look where we've got this, the future is terrific. We can do all these things. And it was wonderful. Everything was so simple and so possible. The sky was the limit.
Suddenly we could do computations the unaided mind never could. Solve problems we had never solved. Just build a bigger computer, and even the unpredictable would be predicted. No more dust bowls. Now we would predict and control the weather. No more economic crashes. With the calculating power of the computer, policymakers believed they could now predict and control the economy, affecting the lives of millions.
They believed that they'd finally now got the theory, got the statistical tools with the power of the computer to once and for all understand how the economy really did operate. Policymakers believed that these were, if you like, laws of economics in the same way that there are laws of physics. I mean, after the traumas of the 30s and the war of in the 40s, the Western economies performed spectacularly well for a very long period of time. It was totally unprecedented prosperity, very low unemployment, and everybody exuded confidence.
Turning in the direction of a new world that symbolizes man's dreams, prophecies, hopes, and aspirations. In the distance we see it.
Government and corporate films confidently portrayed a future of equilibrium, stability, progress, and prosperity. But at the same time that scientists were confidently predicting this flawless future, a meteorologist called Ed Lorenz discovered something in 1962 radically at odds with it. While the military were focused on trying to predict the weather day to day, using vast computers to do it, Lorenz, using an early desk computer, built a simplified model to look at the underlying mathematics, to see if the weather had hidden patterns. Lorenz's discovery came when he ran his model first with one set of numbers, and then again with what he thought were the same numbers, but which the computer had rounded off, making them minutely different.
He put in what he thought were identical numbers, but the starting numbers were different by just a tiny, tiny amount. So there was no reason for him to think that it would actually end up being very different.
What Lorenz found was that the tiny differences in his starting numbers, instead of having no effect, dramatically changed his results.
Things look like they're all carrying on very nicely, and then they suddenly all behave in a very odd way, and the numbers don't do what you think they're going to do. You imagine these two paths going along, and they're just nudging each other, and it becomes a sudden point where suddenly one of them goes off. But actually that happened. The fact that that was going to happen was right back here. It wasn't where it happened.
One of the most fundamental assumptions which every scientist from Newton onwards had made was that a small error in a large system just disappears. It has no consequence. Like a small imperfection in a single part on a long assembly line would make no significant difference to the final outcome. It is this critical assumption which Ed Lorenz's work turned on its head. Lorenz's accidental discovery had tremendous implications for the real world. He could suddenly see that when a system changed, it needn't be because at that moment something had caused it to change. It could be that the seeds of its destruction had been there, slowly growing, hidden in the mathematics all along. The moment the system diverged was the end result of a tiny, unnoticeable change a long time ago. Lorenz had rediscovered what Poincaré had merely glimpsed. He called it the butterfly effect.
So if you have a butterfly flapping its wings, the effect will be very tiny at the beginning. You will see nothing. And then after a while, it will change some fluctuations in the air, some fluctuations in turbulence. And then if you wait long enough, like 6 months, it may have tremendous effects.
The computer, which had been heralded as the engine of stability and certainty, had become the engine of instability and uncertainty.
So computers allowed us to explore things that we used to throw these terms away, you know. Mathematicians say, well, that's too hard, or let's assume it's not important. We can't do that bit, so let's assume it's not important. And you end up with a linear system, which reinforces your view that the world is this kind of quiet place, generally speaking, where nothing really surprising happens and we'll be fine and we just need to know how it works and we can work everything out. To something where the computer allows you to put back in these terms, and Lorenz was basically putting in terms that previously he would have thrown away, and it turns out they changed the system altogether. Certainly its predictability. It's just a brilliant demonstration, accidental demonstration of chaos, really, in the system.
It is the function of the United States Weather Bureau to gather information on such conditions.
The question was, how much chaos was there in the system?
And to give advance warning when human life and property are threatened by high water.
How many aspects of nature did this new mathematics apply to? Was the unstable turbulence of natural phenomena simply because they were complicated, in which case one day we would sort them out? Or were they governed by the sensitivity to initial conditions of the butterfly effect?
Beneath the smoke, the fire will continue to move unchecked through the night.
Just how chaotic should we expect the world to be? And by the late 60s, these suddenly seemed very pertinent questions. In these turbulent times, just as Lyapunov had been drawn to study instability during the Russian Revolution, mathematician David Rouelle was drawn to study the onset of turbulence.
We proposed that hydrodynamic turbulence was associated where there is this sensitive dependence on initial condition. But it happens almost everywhere, that it happens all the time.
Turbulence was thought to arise because of the sheer complexity of the phenomenon. Rouelle, through a combination of experiments and mathematics, proved that turbulence was not the result of complexity, but was caused by the mathematics of sensitivity to initial conditions. The butterfly effect and turbulence were everywhere.
This is not completely a coincidence that I got interested in this problem in 1968. These were the May 68 events. This was an atmosphere where questions were asked that would not normally be asked. The times became ripe because the mathematics was there, because the computers were there, and suddenly there was this enormously interesting experience of interacting with people in different disciplines.
Mathematically, turbulence and chaos were established, and psychologically, were making it harder to pretend the world was still Newtonian. The language of chaos was beginning to enter our vocabulary.
The notion of chaos